Hello YouTube! So I want to give an overview of a paraconsistent logic and I'm going to present the system developed by Graham Priest called the Logic of Paradox, or LP for short. Now there are certain technical points that I'm going to simplify a little bit here. I just want to present this in a brief and accessible way so you have a basic idea of how a paraconsistent logic might work. Right, so first of all, let's remind ourselves of the standard propositional logic. Okay, so in propositional logic we have our propositional variables, P, Q, R and so on, and then our connectives, negation, conjunction, disjunction, conditional, biconditional. And we can consider the truth tables for these connectives. So here they are, standard stuff there. Obviously the biconditional can be defined in terms of these other connectives. So those are our truth tables for propositional logic. And in standard propositional logic we have two truth values. We have 0 representing falsity and 1 representing truth. Okay, then we have a function, the assignment function, which assigns to each propositional variable either 0 or 1, and every such assignment is an interpretation. And we can rephrase the facts of this truth table in this way. We can say that the value of not P is 1 if and only if the value of P is 0, and so on and so forth. That's all the standard stuff. Okay, but that should all be completely familiar. There's nothing surprising there. But I just want us to think about our truth values a bit more precisely. So what we can say is that in standard propositional logic we have a set, which we will call V, of truth values. And obviously the members of that set are 0 and 1. Those are all the truth values we have in our propositional logic. Now I want to introduce another idea. And this is the notion of designated truth values. In standard propositional logic, the designated truth value is 1. That's our set of designated values. So what is this idea of a designated value? Well, we use it to define consequence. We say that some formula A is a semantic consequence of set premises, of set gamma of premises, in propositional logic, of course, if and only if every interpretation that gives the premises a designated value also gives the conclusion a designated value. Now, because standard logic contains only two truth values, truth and falsity, we can simply rephrase this idea as A is a semantic consequence of gamma if and only if every interpretation that makes the premises true also makes the conclusion true. Okay, because we have two truth values, our designated truth value is true, so we can easily just rephrase this rather complicated looking statement in a more commonsensical way. The notion of designated values isn't really necessary for understanding standard propositional logic, doesn't really do any work. But it does become relevant in some of the systems beyond standard logic. Now, let's consider Graham Priest's logic of paradox. So, the logic of paradox contains all the same connectives governed by essentially all the same rules. All we do is add a new truth value. So here are the truth tables for LP. And we can interpret this hash symbol as meaning both 0 and 1. Now technically we haven't actually added a new truth value, but that's how we kind of put it in our truth tables, because we're using the same truth values as we did before. It's just hash represents both of them. So there's just falsity, there's just truth. Hash represents both true and false, both truth and falsity. Now as for our assignment function, well, technically our assignment function isn't a function anymore because hash represents two truth values, and a function can't assign two values. It can't relate to a variable to two values. That's not how functions work. So instead of our assignment function a, we have a relation R which holds between variables and truth values. And hash represents the case when a relation holds between P and truth and P and falsity. Okay then, now we can rephrase our tables in this manner. And we read this as saying, we just read this here as saying that not P relates to 1, or P is true under, or not P is true under R. So this means not P relates to truth, or not P is true under R. So does this work? Does this sort of way of putting it work? Well, let's say that we assign to not P a hash. Okay, this should mean that not P is true under R and false under R. Does the biconditional make sense? Well, if not P is hash, we know by our truth tables for negation that P is hash too. And if P is hash, then P must be false under R, because that's just how hash is defined. Hash includes both truth and falsity. So if P is hash, it's false under R. And since P is false under R, well, not P, by this definition, is true under R. Now, P is also true under R, of course, which means that not P is false under R as well. That means not P is hash. So that all works. And if you go through these other cases, they all work perfectly fine as well. So that's pretty simple. And really, I think that the logic of paradox in general is quite simple, because the logic of paradox just is classical logic, classical propositional logic, except all it does is it removes the requirement that truth and falsity be exclusive. Okay, so for the logic of paradox, it's clear that our set V of truth values is expanded to 0, 1 and hash, and our set D of designated values is 1 and hash. Our definition of semantic consequence in LP is precisely the same as for propositional logic. Semantic consequence obtains, if and only if, on every interpretation in which our premises have a designated value, our conclusion also has a designated value. So if our premises gamma, they're all assigned 1 and A is assigned a hash, well, that argument would be considered valid. So it's clear that in this case, the notion of designated values does real work, since we're not just dealing with truth and falsity, we're dealing with this new value as well, of both true and false. So gamma might be true, and A might be both true and false. The argument is still valid. Arguments are only invalid when gamma is either true or both true and false, but A is false. So that's the case when arguments are invalid. Right, well, I just want to take a little look at this logic at work. Now, I mentioned in the first video how the most famous argument for explosion relies on disjunctive syllogism. Well, what happens to disjunctive syllogism in LP? So a counterexample to this argument is given by an interpretation in which the premises have designated values and the conclusion does not. It turns out this is pretty easy to do. Let's assign P a hash and Q 0. Well, since P is hash and Q is 0, P or Q is hash, by our truth table definition earlier. And since P is hash, not P is hash. And the conclusion Q is 0 just by stipulation there. So there we have it. There's our counterexample. Our premises have designated values and our conclusion does not. So the argument is invalid. Now, disjunctive syllogism isn't the only thing we have to reject. Consider modus ponens. That just came up there. That's just meaning obviously our argument is invalid. But consider modus ponens. Again, let's say that P is hash and Q is 0. So for the conditional here, well, if remember our truth tables earlier, in the truth tables, if we have if hash then 0, then the conditional is hash. So P is hash, Q is 0, that means the conditional as a whole is assigned the hash. If P is hash, not P is hash, and Q again is 0 just by stipulation. So there we have it. Again, designated premises and false conclusion. The conclusion is not designated. So the argument is invalid. This is our counter-example. The argument is invalid. Now the point of all this is just to show you how this logic works. It is difficult to accept that we might have to give up such common inferences as disjunctive syllogism and modus ponens, and so we can certainly debate the value of this logic. But all I'm trying to show you is that it's not difficult to define logics that tolerate contradictions. The moves involved aren't particularly difficult or esoteric. In the next videos, we'll start to examine the deeper philosophical motivations behind this kind of logic. And so yeah, that's about it for today. Thanks for watching, and I'll see you in the next video. Goodbye.